Finally, in section 8, we're talking about electrolytic cells, which are the opposite of galvanic cells. So to just review, galvanic cells utilize spontaneous or thermodynamically favored redox reactions. There is a current produced that can do work. We can talk about negative delta G, and that cell potential, that voltage is positive. So for an electrolytic cell, we're basically going to do the opposite. We're going to force a current through a cell that will, produce a chemical reaction for which that cell potential is negative, and that would be for a non-spontaneous or non-thermodynamically favored reaction. Okay, and we'll call this process electrolysis. This is how we charge a dead battery. So you plug it in right to your outlet, and basically we are, forcing our reaction to go in reverse by using that electricity to charge your battery. Okay, on the left we've got a galvanic cell, anode to cathode for our electron flow, flowing spontaneously from our zinc compartment to our copper compartment. For an electrolytic cell, we're going to have the same components, same compartments. Electrons are still going to flow anode to cathode, okay? But now we have taken the half reaction that was a reduction in the galvanic cell, and now we're making it the oxidation. And the same thing is true for the compartment that was the oxidation in the galvanic cell is now the reduction. And we can do that by applying a power source. And in this particular cell, that power source has to be greater than 1.10 volts to get what would now be a non-spontaneous or non-thermodynamically favored reaction to go. One of the things we are particularly interested in with electrolytic cells or electrolysis is how much metal will plate out in the cathode component or compartment of our electrolytic cell. So in this particular case, how much zinc will plate out as the zinc ion gains electrons and turns into zinc atoms. And that's what we'll talk about next. So if you want to figure out how much of a metal will plate out or how long it would take to plate out a certain mass of metal, we can kind of use this problem-solving process. We're going to use an equation that's in your reference packet that kind of ties together current and time. I equals Q over T. So I is the current, and current is in amps. Q is the charge in coulombs, and T is the time in seconds. So say we know our current and our time, then we can calculate our charge in coulombs. And we have a Faraday constant that ties coulombs to moles of electrons. And then we can look at our particular metal, like if we're looking at copper, let's say, how many moles of electrons are being gained. And then we can relate that to moles of copper, let's say, if that's our metal, and then grams of copper through molar mass. Let's take a look at an example. We're going to determine the mass of copper that plates out when we have a current of 10 amps, and it's passed for 30 minutes. Now we'll want that in seconds through a solution that contains copper ions. So we want to do copper ion to copper metal. We'll start with that equation that has current and charge and time in it, and our current is 10 amps. And 30 minutes in seconds is 1,800 seconds. So remember, 60 seconds in a minute. Our charge is 18,000 coulombs. So now let's do a little factor label. We have 18,000 coulombs, and the Faraday constant is 96,485 coulombs per mole of electrons. Then we can cancel our moles of electrons and go to moles of, well, in this case, it's going to be copper atoms, right? And we're going from a +2 charge to a neutral atom, okay? And so that's going to be 2 moles of electrons that have to be gained in every 1 mole of copper atoms. And then we can cancel our moles of copper and go to grams of copper by using the molar mass from the periodic table, which is 63.55 grams. And then we just have to calculate our answer. 5.93 grams of copper. Now let's say that we want to solve for a time. How long must a current of 5 amps be applied to a solution of silver ions to produce 10.5 grams of silver? So we're kind of going in reverse. We'll start with our 10.5 grams of silver, and we will cancel those grams of silver and go to moles of silver using the molar mass from the periodic table, 107.87. Then we will cancel the moles of silver and go to moles of electrons. And for a silver ion with a +1 charge to become a silver atom, that would be 1 mole of electrons. Then we can cancel our moles of electrons and go to coulombs. That's that Faraday constant, 96,485 coulombs per mole of electrons. And then if you want to stop there with your Coulomb answer and then go into the equation that has current and charge and time, that would be fine. And if you want to rearrange that equation and use it as a factor, that is fine too. But this would be 9,392 coulombs, which I then can plug in to my little equation here. My current is 5 amps, and my charge is 9,392 coulombs, and I can solve for my time in seconds. That is 1,878 seconds. And if you wanted to convert that to minutes, you could. There are, let's see, 60 seconds in a minute and 60 minutes in an hour. That would be 31.3 minutes.